Hello guys, I hope you enjoyed the summer. For today's video I've created a simulation of the cosmos. When creating such a complicated program, chances are that you end up with a program that's never finished. So I've set some clear goals that I want to reach. Show how fast the spaceship would move through the solar system at the speed of light. Make the rotation of the Earth and Moon visible. Show how the seasons affect daylight at the northern and southern hemisphere. And make the size of the Milky Way visible. Let's start with the first question. How fast a spaceship would move if it would move at the speed of light? The speed of light is the fastest speed that's ever possible. In fact, if you have mass like a spaceship has, you're not able to move at exactly the speed of light. But around 10% of the speed of light is probably possible. Currently this spaceship is moving with the speed of Voyager 1, and you can see that it's almost standing still. If we speed it up to 10% the speed of light, you see that the spaceship is now moving really fast and can circle the Earth in just a few seconds. And if we speed it up even further to exactly the speed of light, you can see that the spaceship now circles the Earth very fast. Seen from another angle, it looks like this. So that's really fast. And if we now zoom out, we can see the moon over here. And if we decide to send the spaceship to the moon at the speed of light, you can see that it reaches the moon in just a few seconds. But if we decide to send it to Mars, it'll take much longer. Even at the speed of light, it takes multiple minutes to reach Mars. We zoom out, we see Venus over here and Mars in the other direction. And if I remove the labels, you can see the spaceship over here slowly moving towards Mars. It'll take about 5 minutes. If I speed things up a bit now, let's say we do 1 minute per second, then you can see that after a few minutes we have reached Mars. But you can see that it's already much longer than going to the moon. Actually, if you would go to the sun from the Earth at the speed of light, it would take you 8 minutes. But now if we move to the closest star, Proxima Centauri, you can see how many percent of the distance we have already traveled when we're traveling at the speed of light towards Proxima Centauri. We still need to go a long road before we get there. Actually, it will take more than 4 years, so I will not leave this simulation running for 4 years now. Let's zoom out. Until we see Proxima Centauri. Over here. And now, if we let time pass a lot faster, we can see that the days are passing by really fast and the spaceship is actually now moving towards Proxima Centauri. It's taken already more than 1 year, but it's still at only 25%. It's over there. So you can see the huge distance that our next star is from the Earth. If we would decided to go to the center of the Milky Way, where Sagittarius A is, the black hole, then you can see that even now we're moving at the speed of light and time is passing really fast, it still takes an awful lot amount to get there. Actually, if you would travel at the speed of light and you want to go to the center of the Milky Way, it'll take you about 20,000 years. Our second goal was to show the rotation of the moon around the Earth. The moon circles the Earth 1 time in a month. If we speed up the simulation to 1 month per second, you see that the moon circles the Earth 1 time every second. During its rotation around the Earth, the moon is lit differently by the sun. So sometimes we see a full moon and sometimes we see a half moon. But if we enable trails, you can see how the moon actually moves through the cosmos. Because the moon not only rotates the Earth, but also circles around the sun, just like the Earth. So it makes a really complex movement of circling the Earth and at the same time also circling the sun. So you can see these intertwined trails of the Earth and the moon. Our third goal is to show how seasons affect the daylight at the northern and southern hemisphere. At this moment, if you look at the North Pole area, you will see that if you are standing over here, you will always be lit by the sun, so there is no darkness. The sun is always shining on this part of the Earth during the summer. If you live a little bit more to like over here, then you will move into a part where you go into night. And on this side, on the South Pole, at this moment, you will always stay in darkness if you are in this area. If you are a little bit further out, you will get some daylight. So if we speed up this simulation, you can see that because the Earth is tilted, the sun is shining differently during different times of the year. And here you can see the North Pole going into winter time where there's always darkness. Let's speed it up even a bit more. You can see now we have summer, now we have winter where there's always darkness, and now we have summer again, and so on. Now for our final goal, let's try to show the size of the Milky Way. Starting with Earth, we move away from the Earth. You can see this camera speed increasing, and then we can see our closest planets and the Sun over here. Now if we move further out, we will see the other planets coming. They are much more far away than the rocky planets. And finally we will see Voyager 1, the spaceship that's currently the furthest from Earth. It's already out of our solar system, but it would take another 30,000 years for it to reach the closest star, Proxima Centauri. Let's move out again with speeding up again to show Proxima Centauri, our closest star, but it's not coming very soon. This is already a huge distance. It takes more than 4 years to get there at the speed of light. Then we can see Vega and Betelgeuse, some bright stars that are visible because they are so huge and bright. And finally, we can see all of the Milky Way and the black hole at the center. We are approximately at this position. A quick explanation about how the program was made. I've downloaded models of planets and put them at the proper position. I decided that one world space unit in the editor equals 1 million kilometers in reality. Then I can set the objects at the right distance. Because objects like Mars and Venus are circling the Sun, they contain a script that makes them circle around the Sun. The camera was one of the most difficult things to write a script for. There are a lot of options you have with the camera, but you must be able to see the planets at the right distance. So if you take a look at the camera script, we have a lock on object, and that means that we keep looking at the object itself. This is very useful for studying how the object rotates and moves around. If we deselect this option, you can see that we can now freely look around. We can now move freely around in the cosmos. But if we choose lock on object, we can press forward and back to zoom in or out. It regulates the camera distance to the object. The Earth not only moves around the Sun with this code, but also rotates around its axis with this code. We use the timescale to determine the time of the simulation. We use the timescale to determine how much time has passed in the simulation. Over here you can see the time increased by the timescale times delta time. Also note that some objects are made invisible when the camera is close to the Sun. That's because we don't want to show the very far stars when we are just looking at the solar system. If you would have a simulation and you have a lot of stars in all places of the Milky Way, you would probably need to loop over all the objects and only render the ones that are close enough. Otherwise, it would be a very So that's it for today's video. If you want to try the simulation yourself, or maybe even extend the program and build your own Cosmos simulation, feel free to download the source code with the link in the description. Thanks again for watching, and see you next time.